885 degrees Fahrenheit or 475 degrees Celsius embrittlement damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of 885 degrees Fahrenheit or 475 degrees Celsius embrittlement based on API 571. 885 degrees Fahrenheit or 475 degrees Celsius embrittlement is a loss in toughness due to a metallurgical change that can occur in alloys containing a ferrite phase, as a result of exposure in the temperature range 600 degrees Fahrenheit to 1000 degrees F or 316 degrees Celsius to 540 degrees Celsius. Embrittlement at 885 degrees Fahrenheit or 475 degrees Celsius refers to a degradation process that can occur in certain materials, particularly metals and alloys, when exposed to elevated temperatures for prolonged periods. This temperature range is critical for many engineering materials, particularly those used in high-stress applications, such as in the petroleum and aerospace industries. Mechanisms of 885 degrees Fahrenheit or 475 degrees Celsius embrittlement. Number 1 is grain boundary influence. At this temperature, certain alloys may undergo changes in their microstructure, including grain growth or the precipitation of brittle phases at grain boundaries. This can lead to the weakening of these boundaries, making the material more susceptible to cracking under stress. Number 2 is hydrogen embrittlement. In certain circumstances, exposure to hydrogen, which can be present in environments like oil and gas operations, can further exacerbate embrittlement. Hydrogen atoms can diffuse into the metal lattice and concentrate at defects or grain boundaries, leading to increased fragility. Number 3 is phase transformations. Some materials, particularly carbon steels and stainless steels, may undergo phase transformations at elevated temperatures. For instance, the formation of martensitic phases in steels can significantly alter mechanical properties, leading to a loss of ductility. Manifestations of 885 degrees Fahrenheit or 475 degrees Celsius embrittlement. Number 1 is cracking. The most apparent form of damage seen is the formation of cracks, often originating at grain boundaries or other stress concentrators. Number 2 is loss of ductility. Materials exhibiting embrittlement show a notable reduction in their ability to deform plastically. This may be evident from changes in mechanical properties, such as lower elongation and reduced impact toughness. Number 3 is surface degradation. In cases of environmental embrittlement, surface features such as pitting, spalling, or corrosion may also be observed, exacerbating the material's susceptibility to fracturing. Consequences of 885 degrees Fahrenheit or 475 degrees Celsius embrittlement. The embrittlement process can significantly impact the structural integrity and performance of components, leading to premature failure in service. It is crucial for engineers and designers to consider the potential for embrittlement when choosing materials and designing components that may encounter high-temperature conditions, particularly those that are subjected to cyclic loading or aggressive environments. In conclusion, understanding embrittlement damage at 885 degrees Fahrenheit 475 degrees Celsius is vital for ensuring the reliability and safety of components in high-temperature applications, highlighting the need for careful material selection, design considerations, and ongoing monitoring. 885 degrees Fahrenheit or 475 degrees Celsius embrittlement damage mechanisms affected materials based on API 571. The first is 400 series SS, such as 405, 409, 410, 410S, 430 and 446. The second is duplex stainless steel such as alloys 2205, 2304 and 2507. The embrittlement mechanism that occurs at elevated temperatures, such as 885 degrees Fahrenheit or 475 degrees Celsius, primarily affects several classes of materials, particularly certain alloys and steels. Here are some of the materials and their types that are typically affected by this embrittlement. Number 1 is carbon steels and low alloy steels. These steels can experience embrittlement due to the precipitation of carbides or other phases at high temperatures, which can lead to a reduction in toughness. Number 2 is high-strength low-alloy, HSLA, steels. These materials can also be prone to embrittlement, especially in service conditions that approach or exceed their temperature limits. Number 3 is nickel alloys. Certain nickel-based alloys can suffer from embrittlement due to phase transformations or the formation of detrimental microstructures at elevated temperatures. Number 4 is stainless steels. Some grades of stainless steel, particularly those rich in chromium and nickel, may experience embrittlement through sensitization, especially in the presence of carbon. Number 5 is coated and welded components. Materials that have undergone welding and surface treatments can show embrittlement characteristics due to the localized heating and cooling cycles involved. Number 6 is aluminum alloys. Certain aluminum alloys can exhibit loss of ductility at elevated temperatures. Number 7 is titanium alloys. At elevated temperatures, titanium alloys can also experience embrittlement mechanisms that reduce their toughness and ductility. In general, the embrittlement mechanism at these temperatures is often linked to microstructural changes, such as precipitation of intermetallic phases, grain coarsening, or the depletion of critical alloying elements. Assessing the risk of embrittlement requires careful consideration of the specific alloy composition and the service conditions, including temperature and stress. Critical factors of 885 degrees Fahrenheit or 475 degrees Celsius embrittlement damage mechanism. The embrittlement mechanism occurring at elevated temperatures, such as 885 degrees Fahrenheit or 475 degrees Celsius, is often associated with certain critical factors that can affect materials, particularly in metallurgical contexts. This temperature is notable for its impact on certain alloys, particularly those containing iron, nickel, and other transition metals. Here are some critical factors associated with embrittlement at this temperature. Number 1 is key factors affecting alloy performance include the composition, especially chromium, the amount of ferrite phase, and the operating temperature. Number 2 is more ferrite increases the risk of damage when exposed to high temperatures, causing a significant rise in the temperature at which the material becomes brittle. Number 3 is the time spent at critical temperatures is crucial, as damage builds up due to the formation of an intermetallic phase that is most likely to occur around 885 degrees Fahrenheit or 475 degrees Celsius. It also takes longer to achieve maximum embrittlement at temperatures above or below this point. Number 4 is materials exposed to temperatures between 700 degrees Fahrenheit and 1000 degrees Fahrenheit or 371 degrees Celsius to 538 degrees Celsius are usually considered at risk for embrittlement, especially since it can happen quickly at 885 degrees Fahrenheit. Number 5 is the impact on toughness is not evident at high operating temperatures but becomes important at lower temperatures during shutdowns or restarts. Number 6 is embrittlement can happen due to tempering at high temperatures or by holding or cooling through the temperature range where the transformation occurs. Understanding these factors is essential for material selection, processing, and operation in high-temperature applications to prevent premature failure from embrittlement. 885 degrees Fahrenheit or 475 degrees Celsius embrittlement damage mechanisms affected units or equipment. Embrittlement is a damage mechanism that can occur in certain alloys at high temperatures. This issue can be found in any unit where susceptible alloys are used and exposed to high temperatures, for example, in Number 1 is towers and pipes used in petroleum refining facilities, like fractionators and heat exchangers, especially at temperatures above 885 degrees Fahrenheit or 473 degrees Celsius. Number 2 is certain types of pipes and parts made of stainless steel, which can break when welded, bent, or straightened. Specifically, types 409 and 410 stainless steel are often affected in vacuum towers. Number 3 is heat exchanger tubes made of duplex stainless steel, which can be damaged if exposed to high temperatures, above 600 degrees Fahrenheit or 316 degrees Celsius, for a long time. Appearance or morphology of 885 degrees Fahrenheit or 475 degrees Celsius embrittlement damage mechanisms based on API 517. The first is 885 degrees Fahrenheit. Embrittlement is a metallurgical change that is not readily apparent with metallography but can be confirmed through bend or impact testing, see Figure 4.6. The second is the existence of 885 degrees Fahrenheit. Embrittlement can be identified by an increase in hardness in affected areas. Failure during bend testing or impact testing of samples removed from service is the most positive indicator of 885 degrees Fahrenheit embrittlement. The 885 degrees Fahrenheit or 475 degrees Celsius embrittlement is a type of intergranular cracking mechanism that affects several ferritic and martensitic stainless steels, particularly those containing Cr. The primary morphology of this damage mechanism at 885 degrees Fahrenheit or 475 degrees Celsius is: Number 1 is intergranular Cr depletion. The grains of the metal become depleted of chromium near the grain boundaries, due to the formation of chromium-rich oxides that are driven out of the grain interiors and precipitate near the grain boundaries. Number 2 is Cr-rich precipitates. Alongside the chromium depletion, the grain boundary regions exhibit chromium-rich precipitates, often in the form of fine precipitates. Number 3 is network-like cracking. The intergranular cracking typically manifests as a network-like pattern of cracks, often in a fishbone or sickle shape, along the grain boundaries. Number 4 is no significant oxidation signs. Unlike other high-temperature degradation mechanisms, 885 degrees Fahrenheit or 475 degrees Celsius embrittlement is characterized by very low levels of oxidation, with minimal or no surface scale formation. This unique set of microstructural changes is a key indicator of the 885 degrees Fahrenheit or 475 degrees Celsius embrittlement mechanism, which is often observed in service-exposed components made of susceptible materials. 885 degrees Fahrenheit or 475 degrees Celsius embrittlement damage mechanism prevention and mitigation based on API 571. The first is the best way to prevent 885 degrees Fahrenheit embrittlement is to use low ferrite or non-ferritic alloys, or to avoid exposing the susceptible material to the embrittling range. The second is it is possible to minimize the effects of embrittlement through modifications in the chemical composition of the alloy. However, resistant material may not always be readily available in most commercial forms. The third is 885 degrees Fahrenheit embrittlement is reversible by heat treatment to dissolve precipitates, followed by rapid cooling. The de-embrittling heat treatment temperature is typically 1100 degrees Fahrenheit or 593 degrees Celsius or higher and may not be practical for many equipment items. If the de-embrittled component is exposed to the same service conditions, it will re-embrittle faster than it did initially. Embrittlement at elevated temperatures, such as 885 degrees Fahrenheit, or 475 degrees Celsius, typically occurs in certain materials, particularly specific types of steels and alloys, which can become brittle due to exposure to high temperatures over time. This phenomenon can be attributed to several factors, including the formation of brittle microstructures or the precipitation of damaging phases, like sigma phase in stainless steels. Here are several prevention and mitigation strategies for embrittlement damage. Number 1 is material selection. Choose materials designed to resist embrittlement at high temperatures. Alloys with a good balance of strength and ductility that are specifically formulated for high-temperature applications might be ideal. Number 2 is heat treatment. Proper heat treatment can improve the resistance of materials to embrittlement. This may include quenching and tempering or solution annealing processes tailored to restore ductility. Number 3 is controlled processing. During manufacturing, control the temperature and time of exposure to heat to minimize the risk of embrittlement. This includes minimizing prolonged heating cycles during welding or processing. Number 4 is regular inspection. Implement regular inspection and maintenance of materials exposed to high temperatures. Non-destructive testing techniques can help identify early signs of embrittlement before they result in failure. Number 5 is reduced exposure time. Limit the time materials are exposed to high temperatures whenever possible. This is especially crucial in processes that involve cyclic heating and cooling. Number 6 is post-service assessment. After service, especially if a material has been exposed to prolonged high temperatures, an assessment of its mechanical properties should be conducted to ensure that it hasn't experienced embrittlement. Number 7 is environmental control. Sometimes the environment can exacerbate embrittlement, such as the presence of hydrogen. Controlling the environment and taking steps to minimize hazardous exposure can also be effective. Number 8 is use of protective coatings. Depending on the application, using coatings that can reduce high-temperature oxidation or other reactive environments can help protect the base material. Number 9 is education and training. Ensure that the personnel involved in manufacturing, maintenance, and inspections are educated about the risks of embrittlement and trained in prevention techniques. By combining these strategies, the risk of embrittlement damage at elevated temperatures can be significantly reduced, ensuring the reliability and longevity of materials in high-temperature applications. Inspection and monitoring for 885 degrees Fahrenheit, or 475 degrees Celsius, embrittlement based on API 571. The recommended inspection and monitoring are used to control 885 degrees Fahrenheit, or 475 degrees Celsius, embrittlement are the following. The first is hardness testing. Embrittlement can lead to increased hardness in certain materials. Measuring hardness may help indicate embrittlement, although care must be taken in the correlation to mechanical properties. The second is Charpy impact testing. While not a direct inspection method, performing impact tests on samples can provide quantitative data on the material's toughness and indicate embrittlement. Detecting embrittlement damage in materials, particularly at elevated temperatures like 885 degrees Fahrenheit, or 475 degrees Celsius, requires specialized inspection and monitoring techniques. Here are some inspection and monitoring methods commonly used. Number 1 is visual inspection. This is the simplest method, where inspectors look for visible signs of damage, such as surface cracks, distortion, or discoloration. However, it may not detect internal embrittlement. Number 2 is ultrasonic testing. This method uses high-frequency sound waves to detect internal flaws. Changes in the response can indicate areas of embrittlement or microstructural changes. Number 3 is magnetic particle testing, or MT. This technique is effective for ferromagnetic materials. It involves applying a magnetic field to the material and then applying ferromagnetic particles. Any cracks or discontinuities will attract the particles, making them visible. Number 4 is dye penetrant testing, or PT. This method involves applying a colored dye to the surface of the material. After some time, excess dye is removed, and a developer is applied. The dye that has penetrated cracks or voids becomes visible under UV light. Number 5 is eddy current testing, or ECT. Useful for detecting surface and near-surface defects in conductive materials, eddy currents are induced in the material, and changes in the flow can indicate anomalies. Number 6 is X-ray and gamma-ray radiography. These techniques can identify internal defects through imaging. They are particularly useful for detecting issues in welds and structural components. Number 7 is thermal imaging. This method can identify temperature variations that may indicate structural problems or embrittlement. It can be useful for assessing components that operate at high temperatures. Number 8 is hardness testing. Embrittlement can lead to increased hardness in certain materials. Measuring hardness may help indicate embrittlement, although care must be taken in the correlation to mechanical properties. Number 9 is Charpy impact testing. While not a direct inspection method, performing impact tests on samples can provide quantitative data on the material's toughness and indicate embrittlement. Number 10 is metallographic examination. This involves taking samples from the material and examining them under a microscope. This process can reveal changes in microstructure associated with embrittlement. Number 11 is metallographic examination. This involves taking samples from the material and examining them under a microscope. This process can reveal changes in microstructure associated with embrittlement. To effectively detect embrittlement, it's common to use a combination of these methods: as they provide complementary information about the material condition. Regular monitoring and inspection schedules are key to preventing catastrophic failures in high-temperature service environments. Thank you.